Today, I'll briefly explain Eurocode 7 for deep foundations, especially axially loaded piles. Unlike shallow foundations, pile design really depends on how much data we have, especially the number of boreholes and static load tests. If we have plenty of test results, the design becomes more reliable and less conservative. But if the data are limited, the uncertainty increases. So Eurocode 7 applies larger factors, which makes the design resistance more conservative. So remember, more data, less uncertainty. Less data, more conservative design. According to Eurocode 7, Chapter 7 covers pile foundations. In Eurocode 7, any clause marked with the letter P means it is a principle. Principles are mandatory. There is no alternative. We must follow them. General rules are not preceded by the letter P. They usually use words like should or may, which means some flexibility is allowed. In EC7, external loads are referred to as actions. Actions on foundations include earth pressure and pore water pressure, as well as the weight of soil and water. Of course, we also consider dead loads and live loads. In addition, actions can come from ground movements, such as swelling, shrinkage, or downdrag. Then, our soil properties obtained from field or laboratory tests are the raw data, which will be converted into design parameters in the next step. This slide shows how we move from CP4 to Eurocode 7. Under CP4, we used the allowable stress design method. We mainly worked with allowable loads and a global factor of safety. Under EC7, we used the partial factor method, which is more systematic. For example, load in CP4 becomes action in EC7. Capacity becomes resistance. Ultimate load becomes design action, FD. Ultimate capacity becomes design resistance, RD. We first determined the characteristic values based on a cautious estimate of the data. Then, by applying partial factors, these characteristic values are converted into design values. This slide shows the 3 steps for soil properties in EC7 design. First, from field and laboratory tests, we obtain the soil properties. Second, we select the characteristic values as a cautious estimate of the data. Third, by applying partial factors to the material properties, we obtain the design values of the geotechnical parameters. Under Ultimate Limit State Design for foundations, when we talk about STR, it refers to internal failure or excessive deformation of the structure itself. When we talk about GEO, it refers to shear failure or excessive deformation of the ground. To ensure the stability of the foundation, we must check both STR and GEO limit states. Design Approach 1 is used for foundation design, and it consists of Combination 1 and Combination 2. In geotechnical design, we actually have 3 design approaches. But for foundations, we normally use Design Approach 1. If you look closely at each combination, it consists of actions, materials, and resistance. So we denote them as A, M, and R. The numbers that follow indicate different sets of partial factors applied to the characteristic action, material properties, and resistance to obtain design values. In simple terms, we increase the actions, and we may reduce the soil strength or resistance, depending on the combination, to ensure safety. Eurocode 7 provides all the partial factors for each design combination. For actions or loads, we multiply the loads by the partial factors, depending on whether they are unfavorable or favorable. For soil properties, that is, the characteristic values, we divide them by the partial factors. You'll notice that in Combination 1, the soil properties are generally used as they are. But in Combination 2, the material factors are applied. So the effect of uncertainty in soil properties is taken into account when calculating the bearing resistance. For resistance, we divide the calculated resistance by the partial factors, which are often equal to 1, depending on the combination. As you can see, in Combination 2 for deep foundations, different partial factors are applied to the shaft resistance and the base, or toe, resistance. This figure shows the design procedure we just discussed. First, we assess the design requirements. At the same time, we consider the possible worst-case scenario. Then, we determine the design actions and the design material properties. Using the bearing capacity equations, we calculate the design resistance. Stability-related issues are checked under the ultimate limit state concept. Settlement-related issues are controlled under the serviceability limit state concept. The basic concept of ultimate limit state design is that the total applied loads must be less than the soil resistance. In some countries, a traditional factor of safety approach is used, which is simply the ratio of soil resistance to applied load. Typically, a factor of safety of 3 or 4 was adopted. Nowadays, load and resistance factor design, or LRFD, is widely used in many countries, including Singapore. Eurocode is based on the LRFD method. Unlike the allowable stress design method, LRFD applies partial factors to account for uncertainties in loads, material properties, and resistance. So, in practice, we increase the loads, reduce the material properties, and reduce the soil resistance to ensure safety. Among all these topics, today we will focus on axially loaded piles. In particular, we will look at how to assess the bearing capacity of piles in terms of end bearing resistance and shaft resistance. When designing a pile foundation, several limit states need to be considered. Clause 7.2 lists 11 limit states. The first 7 are ultimate limit states, either geotechnical failure or structural failure. The remaining limit states are mainly related to serviceability, such as excessive settlement, heave, or lateral ground movement. In general, we consider axial loads and horizontal loads as actions. In addition, actions caused by ground movements are particularly important for pile foundations. So soil-structure interaction must be carefully analyzed. In the vertical direction, consolidation settlement may lead to negative skin friction or downdrag, which reduces the available shaft resistance. For geotechnical action analysis, we use Y analysis for lateral loads, Z analysis for shaft resistance, and Z analysis for end bearing under axial load. According to EC7, pile design methods are based directly or indirectly on the results of static load tests, meaning full-scale field load tests. The results from a specific site form the direct basis for the design. If you use calculation methods, your calculations should be verified against field load test results. And when using static load test data, it is important to consider the actual loading conditions, as well as any potential changes in the ground or groundwater conditions. Here, I've summarized the available design methods. Have you noticed some new terminology related to static load tests? We now distinguish between trial piles and working piles. Static load tests can be carried out on either trial piles or working piles. Trial piles are installed purely for testing purposes. It is not always necessary to load them to failure. The ultimate load can be interpreted using methods such as the Davison method, the 10% settlement method, or the Chin method. We'll discuss these methods later. For trial piles, a thorough site investigation is essential to understand the soil conditions around the shaft and beneath the base. Working piles, on the other hand, are part of the permanent foundation. They must be tested to at least the design load. Clause 7.5 describes pile load tests. It covers static load tests, dynamic load tests, the testing procedures, and also the required format of the load test report. According to Design Approach 1, we focus on Combination 2 when calculating pile resistance, using the M1 and R4 partial factors. The partial factors listed under M2 can be applied when calculating unfavorable actions on piles, such as negative skin friction. Clause 7.6 is the core section of EC7 for pile foundations. To demonstrate that the pile foundation can support the design load with adequate safety against compressive failure, the required inequality must be satisfied for all ultimate limit state load cases and load combinations. In simple terms, the design action must be less than or equal to the design resistance. It is also necessary to check vertical displacement to ensure serviceability of the supported structure. The design load, FCD, is determined from combinations of actions following the partial factor method. It includes the self-weight of the pile. The design resistance, RCD, can be determined from static load tests, dynamic load tests, or ground test results. It includes the overburden pressure of the soil. However, note that the pile's self-weight and the overburden pressure may be disregarded if they approximately cancel each other out. Let's take a look at how to evaluate the design resistance. The design resistance of a pile, RCD, is the sum of the base resistance and the shaft resistance. In EC7, this design resistance is factored using partial factors, typically gamma factors for shaft and base resistance. The left equation is normally used when we design by calculation, where shaft and base resistances are evaluated separately. The right equation is used when the shaft and base components cannot be determined separately. The differences in partial factors between driven piles, board piles, and CFA piles mainly reflect the increasing probability of unexpected effects during installation, which may influence the final bearing capacity. This table summarizes the partial factors, action factors, material factors, which are mostly equal to 1, and resistance factors for driven and board piles. The Singapore National Annex allows different R4 values, depending on whether serviceability has been verified. So if there is no pile load testing and we rely only on calculation, a higher resistance factor must be used, meaning the design becomes more conservative. Let's go through the method based on static load tests. We use the compressive resistance, RCM, measured from static load tests on trial piles. The characteristic compressive resistance, RCK, is calculated using the given relationship. First, we determine the measured mean value and the measured minimum value. Then, we apply correlation factors, Xi1 and Xi2. These correlation factors depend on the number of piles tested. So, the more piles we test, the smaller the uncertainty, and the less conservative the result. After that, the characteristic compressive resistance must be divided by the resistance partial factors to obtain the design resistance. If necessary, the characteristic compressive resistance, RCK, can be separated into the characteristic shaft resistance, RSK, and the characteristic base resistance, RBK. This is possible when we use fully instrumented test piles, where the shaft and base contributions can be measured separately. In addition to static load tests, the variability of the ground must also be considered when assessing the characteristic compressive resistance. There are two procedures to account for ground variability: the model pile method and the alternative procedure. In this method, the ground test results at each individual profile are used to calculate the compressive resistance of a model pile at the same location. Then, correlation factors are applied to the calculated resistance to account for the variability of pile resistance. The resulting factored value is taken as the characteristic compressive resistance. The calculated compressive resistance, RCcal, can be determined using prediction methods, such as the equations we discussed, based on ground test results. As you can see, the calculated mean value or the calculated minimum value can be estimated independently. These values are then factored using correlation factors, Xi3 and Xi4. Here, we calculate the compressive resistance using equations based on ground test results. To calibrate the results and account for variability, we apply correlation factors, which gives us the characteristic compressive resistance. Finally, by applying the resistance partial factors, we obtain the design compressive resistance. Let's now talk about the alternative procedure. As an alternative to the model pile method, EC7 allows the characteristic base resistance, RBK, and shaft resistance, RSK, to be determined directly from ground parameters. In this case, to account for the additional uncertainty in direct calculation, a model factor is introduced. The value of this model factor is specified in the National Annex. This slide shows the flowchart for the model pile method and the alternative procedure. If we have more than one set of ground test results, we can use the model pile method, applying correlation factors and then partial factors. If data are limited and we have only one ground test result, we use the alternative procedure. In that case, we apply a model factor and then the partial factors to obtain the design compressive resistance. Similar to static load tests, we can also obtain the characteristic compressive resistance from dynamic load tests. Of course, we still need to apply correlation factors, Xi5 and Xi6, to account for uncertainty and variability. As you can see, Xi and Xi2 are used for the static load test method. Xi3 and Xi4 are used for the model pile method. For dynamic load tests, we apply Xi5 and Xi6. And for the alternative procedure, instead of correlation factors, we apply a model factor. Here, I've summarized the correlation factors with respect to the different design approaches. In the next session, we'll go through some typical examples of pile design. So please stay tuned. Thank you.